Hello and welcome to Numeristical. We are continuing our series on baseball prediction. We are now in the 11th video of the series. And in the last video, if you'll remember, we added lineup-based features to the model. And again, got a small improvement, but still we're about 30 basis points off the Las Vegas model for predicting the winner. At the conclusion of that video, we decided the next step would be to change gears a little bit and try to see if we could come up with a model for predicting the number of runs scored by each particular team in a game. And the idea behind this was it would be useful for two reasons. One would be that we could predict the over-under. So if we know how many runs each team scores, add them together, get how many runs are scored in the game, and see if we have any edge against Vegas in predicting that. And then secondly, this also might be useful for predicting the overall winner of the game, because we have this sort of middle point. We know that how does having good hitting help you win the game? It helps you by making you score more runs. So maybe let's predict the number of runs scored, and then come up with a second model that says, given those runs scored, let's figure out how likely you are to win the game. So that's where we're headed. So to do that, we got to do a couple things. We have to first do some wrangling of our data to get the data in a form where we have, here's a bunch of teams hitting features, here's the other team's pitching features, and here's the run scored by the hitting team. So we're going to do some data wrangling to get it into that. And then second, we're going to start modeling. We'll build our first model, and we'll use something called probabilistic regression, and specifically this algorithm I've developed called Coarsage. And essentially what that will do is be able to predict distributions on the number of runs scored. So rather than just saying the average number of runs scored is going to be 3.2, we're going to actually have probabilities of 0, 1, 2, 3, 4, 5, and so on. Exact probabilities on how many runs scored we think there will be in this game. So that's where we're headed. Before we go ahead into the notebooks, I'd like to ask you again to please like this video and subscribe to the channel if you haven't already done so. And with that said, let's go into the notebook. Okay, so to reiterate, we're switching our focus onto predicting runs scored, and we're gonna use this for both the over/under and then eventually to go back to the game winner and see if this will help us come up with good features for predicting the game winner. And we're gonna focus on predicting the distribution of runs scored. So we don't just want a point estimate in average. We want to know what's the probability they'll be shut out, what's the probability they'll score exactly 1 run, probability they'll score exactly 2 runs, and so forth. So predicting the distribution of a numeric target variable, this is called probabilistic regression in the literature. So in this notebook, we're first going to wrangle our data. So we need to get our data in this form so that we have the features that we want and the target that we want in each row. And once we get that, we'll go into the second notebook where we'll start building a model to predict the number of runs scored. So let's get moving. So we're going to import our usual stuff. We're going to load in our previous data frame. And now, what's our goal? So we want to split each game. If we think about each game, you can think of it as 2 halves. You've got a set of hitters against a set of pitchers, and we know how many runs those hitters scored against those pitchers. And then you can think of it as almost a completely separate thing. It's a completely separate thing. We're going to have the other team's hitters versus the opposite team's pitchers, and they scored a certain number of runs. So we're going to split each game into 2 rows. One where the home team bats against the visiting pitchers, and we're trying to break the runs of the home team. And then another where it's the visiting team batting against the home team's pitchers, and we're trying to predict the runs of the visiting team. So when we do this modeling, we're actually going to be splitting each game into 2 rows. So how are we going to do that? Well, first I'm going to define a bunch of columns. I call these reference columns. So these are columns I want to carry around either because they have the odds, because they're just identifiers about the game, the names of the teams, the date of the game, so forth. And the idea is that these columns don't care about which team was the visitor team or which team was the home team, for the most part. And you'll see what I mean, I think, as we go forward. And then our targets are going to be the home team's number of runs and the visiting team's number of runs. And here in these next two cells, we're going to do just a bit of programming to come up with groups of names of features. So here you see I've got the stems. So for team hitting, these are kind of the stems that we're worried about, like the main feature without worrying about the window size or which team we're talking about. We've got the lineup features. So these are going to be the features we get from finding the individual batter performance and then averaging them across the lineup. Then we've got the starting pitching stems, the bullpen stems. Here we define the window sizes for each of those categories of features. And then over here, we're going to just iterate out all the different names of the features that we have. So this is just a big list comprehension where we iterate through the window sizes, and we're going to have two kinds. We're going to have an A set and a B set. So in the A set, the home team is hitting and the visiting team is pitching. So we pick out those particular features: the hitting features for the home team, and the pitching features for the visiting team. And in version B, we switch the roles of home and visiting. So let's just run these cells again. This is just bookkeeping to come up with lists of names of features. So now, what's my strategy going to be? I want to come up with an A data frame, which says, here's the home team's hitting, the visiting team's pitching, and the number of runs the home team scored. And then we're going to have the B data frame, where we switch the roles of home and visiting. But then what we want to do is we actually want to strip out whether it's home or visiting. We don't really care which one is home and which one is visiting. We just want to say the hitting team had these hitting statistics, the pitching team had these pitching statistics, and here's how many runs the hitting team scored. So, so that's what we do here. We say, okay, the columns A, we're going to take the reference columns. The reference columns we always want to carry around. We've got the number of runs of the home team, the hitting features, and the pitching features for group A. So these will be the home hitting features and the visiting pitching features. And I'm going to make a data frame out of these columns. And I'm going to add a new column that says, a new column called home hitting. I'm going to say it's 1, so it's to indicate that in these rows it's the home team that's batting, because we might want to carry that around to know whether it's the home team batting or the visiting team batting. Likewise, on this side, we're going to come up with our B data frame. It's the same thing, except now it's the run score to the visiting team and the visiting hitters and the home team pitchers. We come up with that data frame. We add in this column saying that home hitting is 0. And now we strip the feature. So any of our features that had an underscore H or underscore V on it, now we want to get rid of those, because we're going to put this all together in one big data frame. So we need one column name for all of those. So what's going to be, what was a combination of some entries from the home column and some entries from the visiting column is now going to become one column. And this is going to be our final column list. And we're going to assign this column list, these names of columns. We're going to rename the columns of DFA and DFB, basically stripping out the underscore H and underscore V where it's appropriate. And then we're going to put it all together. So run that. So what happens when we're done, if you just pick 5 random rows, you'll see we've got our initial columns, season, date, the teams that are playing, what league they are, the over-under line. These are all old games, so we don't actually have any of the odds. If these were more recent games, you might see the odds results here. The ballpark, day game or night game. Here's the runs scored. So this is the run scored of sort of the batting team. And here are all the statistics we have about the batting team. And you'll see there's no underscore H or underscore V here because it's just the batting team and the pitching team. So we've got all the statistics for batting. We keep going, all the statistics for pitching, and then we've got this last column that says whether this is a row where the home team is batting or a row where the visiting team is batting. So we've got the 0, 1. So this is our data frame. And so now, if we want to model runs scored, we can use all of these features, and we're trying to predict this one column, runs. This is what we're trying to predict. How many runs are scored when you have a hitting team that has this quality and a pitching team that has this quality, and it's the home team that's hitting, or it's the visiting team that's hitting. So we're going to save that off. It'll take a little while to save. But while we're doing that, let's go over to the next notebook. So now we want to actually try to predict the number of runs scored. We're going to build a model. And as we said before, we're going to try to predict the distribution of the number of runs scored. And we're going to use this algorithm called Coarsage. This is something I've come up with. It's in the StructureBoost package. It's still relatively new, so you might find bugs in the package and so forth. Coarsage is similar to PrestaBoost. PrestaBoost is something I came up with a little earlier, and then Coarsage is kind of a more advanced version of it. But there's a paper on PrestaBoost that you can find over here if you want to click this link and really dig into details. This is a more sort of academic style paper. But Coarsage is a bit cleaner. PrestaBoost basically you do multiple gradient boosting models and average them. And Coarsage essentially achieves the same effect but does it with a single forest. I have not yet written a paper on Coarsage that's on my to-do list, but it might be a while before I get around to it. But again, what makes this different from regression problems we've probably worked on is that we're trying to get a distribution. We don't just want to say, on average, this team scores 3.2 runs. We want to know what's the probability of 0, what's the probability of 1, what's the probability of 2, and so forth, all the way out to some maximum value, which we'll figure out what that should be. So let's get started. To use this, you're going to need to upgrade to the latest version of StructureBoost. So you want to make sure you're on StructureBoost at least 0.4.0. So you'll probably want to uncomment this command and run it, which will upgrade your version of StructureBoost. So we'll import these packages. So it should say 0.4.0 or later. If it doesn't, then this won't run. And now we're going to load in both data frames. We're going to load in our original data frame and also this data frame that we just made in the previous notebook. So let's do that. Okay, so it's loaded them in. Now, as I said, we're doing this probabilistic regression, so we're trying to predict the distribution. One of the questions we have is we don't want to go out to what's the probability of 35 runs, 112 runs scored, right? At a certain point, we got to say, okay, this is high enough, and we're just going to lump everything bigger than this value into one final category. So the way I've decided to choose what that number is, I said, let's look at the over-under line and see what's the maximum for that. Now, that's the over-under line for a whole game. But the idea is for predicting the over-under, right? If the over-under is, let's say, 12, you want to know, knowing the probability that a team will score like 9, 10, 11, 12 runs, those are going to be important numbers. But once you get past 12, it doesn't really matter. Once a team scored 12 or more, you don't really care what particular value it was because you know you're over. If one team scores 12, then you know you're over. So what I'm going to do is I'm going to look at the over-under line for the games that we have and say, what's the max over-under? So the max over-under was 15. So that means that for predicting the over-under, we're never really going to care whether a team scored 15 runs versus 18 runs. Because once they scored 15 runs, we know that we've hit the over. So I'm going to use that just as a judgment call, as a heuristic, to say, let's cap the number of runs, set a ceiling at 15. So if you scored more than 15, I'm just going to call it 15. So I'm going to come up with a new variable called runs trunk for truncated. And I'm going to basically say, if you're more than 15, just call it 15. And now we're going to break up this df runs, this is the new data frame we created in the last notebook, into train, valid, and test sets, same as we had before. And I'm also just going to splice out, or actually not going to use this right now, but splice out the test set of our original notebook, the game level notebook. So again, if we just look at this df runs table, you'll see as before, we've got these sort of reference columns tell us the date of the game and so forth. And then we've got these columns. This is the head, so some of these are not in numbers. But you see we have these hitting features and the pitching features, and which is the home team, and then this runs truncated where we just set a cap of 15. So as a feature set, to start this off, I'm going to take the same features that we did in our last model, so our sort of best model to date for predicting the winner of the game. I'm going to take that and take off the home and visiting teams, because right now we're just saying here's one particular home, here's one particular set of batters, here's one particular set of pitchers. Let's try to predict how many runs scored will generate from this clash of these two sides. Now, we're going to use this Coarsage thing. So Coarsage is essentially like gradient boosting. It works in that same way of sort of building trees, calculating the gradient of a loss function, and then trying to use the next tree to predict those gradients. But the idea is you have to, there's a few ways to use it. The way we're going to use it in this case is we're going to set up particular bin points. And in this case, this is an easy choice because what we want to know is it in which of these bins, defined by these bin points, is the true answer. So is it between negative 0.5 and 0.5? That means is the value 0, then it's between negative 0.5 and 0.5. If the value is 1, it's between 0.5 and 1.5 and so forth. So in this variant of Coarsage, we're going to fix the bin points. So we've got essentially 16 bins. We've got 17 bin points. They define 16 bins. Those 16 bins are from 0 to 15. Remember, 15 is our maximum, so anything bigger than 15 is treated as 15. And we want this algorithm to sort of go through and figure out, for a particular set of features, what do we think the distribution is over these 16 bins. Give me a probability that it's in each of these 16 bins. So we're going to use as our target variable this runs truncated. And again, we're going to define our x's to be the feature sets and our y's to be the target. And we're going to run this Coarsage. And I don't have time to get into all the variants of Coarsage and all the different ways it works. But there's some, if you do a Shift-Tab, you'll see there's a fair amount of documentation that will explain how all of this works. If you're really interested, you can read the paper on StructureBoost. That'll at least help you understand some of these terms. But essentially what we're saying is 1,000 trees, this is all similar to regular gradient boosting. I'm doing a higher max depth because in general for this probabilistic regression, you typically want deeper trees because it actually has a multivariate output. So whereas before we just had yes or no, now we've got 16 different possibilities for the right answer. So it typically calls for deeper trees. And our bin point method is fixed, and we gave it this bin point vector. Now, there are other variants where if you're just predicting something and it's more continuous and you don't really know the range of it, you want it to sort of learn everything from data, you can pick different options that'll try to learn the bin points from data and won't fix them. But in this case, we kind of know the bins we want, so this is well suited for what we want to do. And we're going to run this. So this is somewhat slow to run, so I'm going to fast forward to the end here, but it's doing a lot more than a standard boosting thing because it's trying to predict out a whole distribution and not just a single point estimate. So I'll fast forward to the end where we get to see the results of this model. Okay, so we're done. We finished up. That took about 10, 12 minutes to run, something like that, to train. And you can see as we do with regular gradient boosting, we used an evaluation set, and we told it to keep training until you didn't reach a new low on your evaluation set for 5 steps. So you can see that we got better until here, and then we had 5 steps in a row. We never quite achieved what we achieved over here, so it stopped. So now we're done training the model. So now we can make predictions. Now, predictions work a little differently here because we're predicting distributions, but we can still evaluate the log loss, and we get 2.42. Now, it's hard to know what, if anything, that means. Right now, it's only going to be really useful for comparing models to each other. But the log loss is the same concept as before. It's the log of the predicted probability of the true outcome. So it's essentially the log likelihood. You'll notice the number is bigger here. The reason why it's, before we would have numbers that were less than 1, and now we've got 2.42. The reason for that is that we now have 16 possible outcomes. So thought of in terms of entropy, if you think of an entropy framework, there's a lot more entropy. There's a lot more uncertainty because there's now 16 possibilities for the right answer as opposed to just 2. So what we can do now with this is we can plot, I'm going to take the first 6 points in our test set and plot the predicted densities and also plot what the true value ended up being for that particular case. So this is the first one of the test set, and you can see that this predicted about a 9% probability of a shutout, about a 15% probability of exactly 1 run, maybe like a 17% of 2 runs, 16% for 3 runs, and so forth down. You see this little bump up for 15, right? Because 15 aggregates 15 and bigger. So that's why actually the probability for 15 is higher than for 14, is because 15 also incorporates anything bigger than 15. And you see for this particular game, 6 was the true number of runs. So when we're calculating that log loss number, what we're doing is finding the true value, getting this probability, and taking the log of it, and then we're averaging those values across everything, across the test set. And then it's the negative log, actually. So here you can see these things they look very similar, but you see they do have different shapes, right? So first of all, if you look at the probability of a shutout, so like on this one, it's 10% probability of a shutout, and in fact that game was a shutout. And the maximum's at 2. So the single most likely outcome was for only 2 runs. Whereas, for this game, this is a much more high scoring prediction, right? They had only a 6% chance of a shutout, and the highest value is for 3 runs. And you see the probabilities of these bigger numbers are actually higher, and if you overlay them, you'd kind of see that better. But you could even see it comparing this one to the one above it. You could see this drops off much more quickly, and this kind of goes down a little bit more slowly. So this is what a prediction of kind of a more high-scoring game looks like, and here's what a prediction of a more low-scoring game looks like. So what can we do next? We've got this model. Now I can play around with this model, try to improve that log loss, and see what combination of features and stuff improves things. But it'll be a little better to evaluate these. It'd probably be a little better to go all the way to the end and see, okay, what kinds of predictions did these lead to for the over-under and so forth. So to do that, we got to do a couple things. So we're going to have to, what are our next steps? We're not going to get to this video. But now we've got a model, and we can play around with the model and improve it, but we've got a way that you give me the features of a set, you give me the hitting features and the pitching features, and I can tell you, here's the probability I think of it, how many runs are going to be scored for every possible number of runs scored from 0 to 15. Now, if I give you a game, I could say, okay, for the home hitting and the visiting pitching, here's how many runs I think the home team will score and the probabilities associated with each of those possibilities. And likewise, when the visiting team hits, here's how many runs I think they're going to score, that distribution. I can put those two distributions together now. I can add two probability distributions and get a distribution on the number of runs total in the game. And then once I do that, I have a probability distribution on the total number of runs in the game. I can look at the over-under line and say, what's the probability I'm less than the over-under line? What's the probability I'm more than the over-under line? What's the probability I'm exactly on the over-under line if it's an integer number? And using that, we can then compare to Vegas and say whether or not we think we can make money on this. So that's what we're going to do next. Next, we're going to take just this first model and come up with a framework for how can we evaluate whether we have an edge, whether we can actually make money on this. We're going to turn these team level run predictions into game level total run predictions, and then turn those into how likely do we think the over is going to hit versus the under, and then we can evaluate that. So we've got a lot more to do, but stay tuned. I think it's going to be pretty exciting. So I hope you'll join me as we continue forward. Once again, thanks for joining me today. If you can, it would really help me out if you could like this video and subscribe to the channel. Again, next video, we will push this forward. We will turn these team level predictions into predictions about the total number of runs for the game and compare them to the over-under lines and really try to evaluate, hey, do we actually have an edge on Vegas with this model? Can we actually make money? And we'll see. It's the analysis can be quite involved to really convince yourselves whether or not you're onto something, whether or not you could actually beat Vegas with this particular model. So I hope you can continue to join me and have a great day.